Tell him to wait. 2 minutes, Anup.
A very warm welcome to you, Dr. Preeta Sharan.
Thank you.
In this session, Dr. Preeta Sharan will deliver the talk on Design and Photonics Sensors in Biomedical Healthcare. I would like to introduce Dr. Preeta Sharan to the participants. Dr. Preeta Sharan is a professor in the Department of Electronics and Communication Engineering in the Oxford College of Engineering, Bangalore. She has completed postdoctorate from IIT Kharagpur, PhD from IIT Banaras Hindu University, and currently a competent professor with 22 plus years of experience in education, research, student membership in association with international universities and organizations. Responsible for teaching BTech, MTech students and guided 6 PhD students and executed government and international agency funded projects. A self-starter with strong entrepreneurship spirit and built R&D center of her own with team size 15 plus from scratch. She has delivered projects for prestigious funding agencies across the world as lead investigator like Naval Research, DRDO, IEEE USA and Government of Karnataka and AICTE with multiple patents in process. Recent publications reaching 100 plus under her leadership. Visited faculties of leading universities, NTU, Singapore, Tohoku University, Japan, and University of Macau, Limerick University, Ireland. And she has published papers in premier journals and presented papers in IEEE conferences in Malaysia, Singapore, Japan, and Macau, and delivered lectures for VTU Learn e-learning program through satellite for country-wide classroom. And she has successfully conducted workshops in collaboration with IIT Delhi and IIT Bombay. She is primarily focal point and owner for all activities in her college as IEEE student branch counselor and site coordinator, and also associated with IEEE Humanitarian Technology Group. Recently developed device concept for physically disabled person to operate computer-backed best design award in International IEEE IMA Conference 2015. Awarded Woman of the Year 1998-2009 by American Biographical Institute. Associated with Elsevier and Macro Health publication as reviewer. So this is about Dr. Preeta Sharan. So once again, welcome back, ma'am. You can take over the session now, please.
Thank you. Thank you. I will share my slide. My slide is visible? Hello?
Yes, madam. It's visible.
Yeah, it's visible now, no?
Yes, madam. Clearly visible.
Okay, fine. Okay, so thank you, Triveni madam, once again for giving me this opportunity. So today's topic is design of photonic sensor in biomedical healthcare. So what I have done in my talk, during my talk, I have taken all possible biomedical healthcare, whatever we have done in the photonics, so that it will give wide scope for any other researcher to work towards this. because only photonic crystal sensor I have not taken. I have taken MEMS, I have taken SPR. So what are the possibility in the photonic sensor which can be applicable in biomedical healthcare? I have tried to explain you. Today I am going to explain you. So few slides before I am showing, just to motivational slides I can say. This is my research center in my research area, because whenever I used to give talk, I am always open for collaboration. So why I am showing this? These are my research area. So anyone from the attendee side, if they want to collaborate, because of giving talk, I will tell you, my network is very wide actually now. What happened from Orissa to Punjab and up to Himachal Pradesh. So some of the attendee afterwards they will take some of my phone number and they will call me and they will tell that I am working in optical network side, I am working in quantum communication, I am working in optical MEMS. So in this way, what happened? Lot of benefits and share of knowledge we are doing. That is the reason I used to show few slides before starting. These are my research area where each area two PhD students are deployed and they are doing PhD, and obviously because of PhD MTech and then BTech students. So set of people are working in each area. This is the beauty, and these are the few achievement which I am very proud to say, that 6 PhD students pass out, graduated, and 7 are pursuing, and funding I got till now, it crossed 1 crore 67 lakh funding, because of government funding agency are very kind enough to give, and it's very easy. Anyone who are doing little bit work, they can apply for funding, and you will get funding. It's very easy, and out of this funding, all those things you can see that lot of awards and all are there, and this is the Scopus metric. Yesterday I took, so 93 document are showing in the Scopus metric, and citation 482, H index 13, SCI journal 18. Here you can see. Yesterday I took 98. It is showing in the Scopus. All SCI are Scopus. This just 2 minutes. I will finish it off. Now I will start my talk. Fine. So today's topic is photonic sensor for biomedical healthcare application. So first, what is photonic sensor? I was listening talk of Srinivas sir. So I was going through that what he is talking, so that I should not talk that for that reason. And as per that, I have modified my slide just now. So optical sensor. So some basic I want to give, because I was seeing that he has gone directly to the device level. So some basic I want to give, that why do we need photonics instead of electronics? So I think this FDP is for the photonic only, photonic and quantum. So till now you understood that speed of light is very high, first thing. Second thing is it is insulating in material, insulating material. So because it is not conductor, so what happened? EMI, we can save our device with the EMI effect, and its size is very small, so can pack more wavelength and allow large transmission bandwidth, because whenever we are talking light, it means that bandwidth is very high. Okay, 10 to the power 14 to 10 to the power 17. So it's very high bandwidth frequency we are having, and it is very portable. So now what is photonic crystal? As I told, when we are talking photonic technology, photonic sensor, this photonic is a grandfather, you can say. Then this photonic is further divided into different type of sensor. We can take photonic crystal as a sensor, we can take SPR as a sensor, we can take optical MEMS or MOEMs as a sensor. Okay, so fiber Bragg grating as a sensor. So these are four. I am talking about four, but microfluidic also is there. So these 5, 6 domains are there in the photonic. So anyone who is interested to do research, they can go in anyone. or else they can take one from each and they can do research. This is also very good idea I'm giving you for doing the taking the research topic, because nowadays people are wondering that what topic I should take. So quickly I will go. What is photonic crystal? Photonic crystal, you can see there are two structure, rod in air and holes in slab. So the name photonic crystal is nothing but it is a periodically varying waveguide. Periodically varying means dielectric constant is periodically varying. You can see here, this is photo etching. By doing the photo etching you will get the structure, and this is doing the FIB technique, focused ion beam lithography technique. So by using the FIB technique you will get this structure. This is known as the holes in slab structure. Okay, then, why photonic crystal act as a sensor? This is an important question. How it act as a sensor? It will be clear with the wave equation. And now configuration of photonic crystal. There are two configurations. So we can use either the point defect or we can use the line defect. Depend on the application. So if you are removing one rod here from this center yellow color, then it is known as the point defect. If you are removing one line from here, it is known as the line defect. So you may ask which application point defect. Suppose if you have to find out E. coli bacteria in a water, so dimension of the E. coli bacteria, that dimension you can create in writing the MIP code using operating system Ubuntu. So that particular dimension we will take the rod size, so that that dimension bacteria will struck there, and then you will allow light to pass, and other end you will get the signature graph, okay, which we will maintain in database. And suppose if you are taking blood sample, urine sample, then go for the line defect. Okay, and now types of photonic crystal. This is very known fact: 1D, 2D and 3D. If light propagation is towards one dimension, it's called 1D, and light propagation is towards two dimension. And then lattice means how this top, how dots, you can see dots are arranged. If it is arranged in the square fashion, it is known as the square lattice. If it is arranged in the hexagonal fashion, you can see this, so it is known as the hexagonal lattice. This also depends on the application, which application you are working, which it depends. Mostly people are using hexagonal lattice to avoid the losses, fine, in their structure. And you can see that we have created one defect and we have created the line defect. These two are the basic defect engineering. So this how we have created. We have taken the meep tool. Meep tool is an open source tool, and using meep tool you can write the code for this, and you can create the defect engineering. And line defect also you can write a code in the meep tool, and you can do either. These are the open source where you have to write the code. When you have the software simulator like rsoft or Lumeric software, then you can write the symbol will come. In that you have to give the pop-up window will come, where you have to assign the values. It will be easy. So now few work towards photonic crystal I will show, and all standard paper. This is IEEE transaction paper accepted. So here what we have done: an analysis and design of photonic crystal based biochip for detection of glycosuria. So glycosuria is a disease for diabetic patient, okay, where it will damage the eyesight also. So my first PhD student, she worked towards the diabetic patient, and she has taken the RI value, refractive index value of the type 1 sugar concentration, type 2 sugar concentration, and type 3 sugar concentration. So during her PhD, what she has found out, total PhD was based on the uh, diabetic patient. So she has found out the first level. She has found out in the blood sample how much is the sugar concentration. Okay, and then what happened? Suppose patient will go to the doctor. Doctor will give the oral medicine, and they will advise for the take the medicine and lifestyle. And patient has not understood. well, and second time again he went to the doctor. That time doctor will see the prescription of the first time, and second time he will suggest patient go for the urine test. So if urine test your sugar concentration value is x1, it means in blood test it will come 2x1. Okay, so all those things are from the medical point of view. Now what we are doing, we are our vision is to create a device where patient can randomly check whenever they want. So for that reason, we have created here line defect. Okay, say holes in here slab structure, holes in slab structure, and you can see here that light is allowed to pass, and light is passing from one end to other end, and you can see this is the optimized result. To get this result, lot of iteration has to be done in order to confine the light here. Okay, and then here you can put your urine sample, the blood sample, and at the other end you will get the signature graph. And these are the parameters which we have considered. Hexagonal lattice structure, A is 1, A between the two, and dielectric constant of silicon slab is 12, and these are the parameters for writing the code. Okay, so you can see that we have taken glucose analysis in urine sample. It means type 2. One is for the sugar sample. Now you are taking in the urine sample. In urine sample, what you are observing from 0 to 15 mg per dl, if it is okay, then it is, suppose if you are normal, if don't you are not suffering from diabetes, then the sugar concentration should be 0 to 15 milligram per deciliter of the urine sample. Then RA value was this. But if it is 0.625 gram, it's not milligram. See, 0.625 gram per dl, 1.25 gram per dl, it means sugar concentration increases. It means that you are pakka diabetic person. This we got from literature survey. Okay, and then we have allowed light to pass, and we have seen the normalized transmitted output and transmitted frequency and power we have calculated. So you can see that blue color, the first graph, clear cut distinguished shift we are getting for the normal person, means the person who is not suffering with the blood sugar, and all other with the person is suffering from the diabetic. So you can see that this is maintained, and I have not done the zoom graph. If you will do zoom graph, then you can see a distinct shift. What extra we have done apart from this photonic sensor, now as time advance of my first PhD student, now I am in the sixth and seventh PhD student under me. Here we are using the machine learning. That part I am not showing you because today's topic is totally based on the photonics. If you will use the machine learning, then it will classify the each concentration, and very neat graph you will get by using the MATLAB code. A lot of classifiers are there, naive-Bayes classifier, then AdaBoost classifier, lot of classifiers are there. By using that, you can distinguish each and every shift, so that and not only that we stop, we further went for the Raspberry Pi, where we can showing the display. Okay, for the each, means if you have this much sugar concentration, so this is the signature graph. I want to say that end to end product I have done prototype in my lab. This is a simulation design for glucose analysis, the blood sample. So blood sample also we got the refractive index value, and then we have allowed light to pass, and we have seen the transmitted output. And you can see that again here blue color is for the normal, and all other different colors are there for the person who are diabetic. It means sugar concentration is more. Then see, if you are interested to many people will say that my paper is not accepting in the transaction, it is very tough. Transaction means some novelty you have to give. So what novelty we have given? Photonic crystal many people are working, but end to end product you are, if you want to see that, you will not get. They will say that this some other person will do. So what we have done, the Python background based IPCAS software is there. This we have taken, and we have made the, you can see that this looks like a chip. So now we are ready with the GDS2. So if we will give this layout to foundry in Belgium, IMAC, so they will directly fabricate this. This information we got from IMAC Belgium. So these are the things GDS2 is required, as it is in the same pattern as a VLSI people are doing. They are also designing in the by using the cadence tool, and then at the end they will give the finally they have to give the GDS2, so that in Taiwan foundry they will fabricate. So same step I have followed. Okay, so this was this looks like a chip only. You can see that two port are there, input port and output port. So it should be it is ready for fabrication. That's why this paper was accepted in that IEEE transaction sensor and actuator journal. Okay, and this second paper was optics communication. All SCI papers are there. So this topic was design of photonic crystal based ring resonator for detection of different blood constitution. Okay, so what happened in this, what we have done, I'll tell you. In our blood sample, if we will take blood, then we have RBC, WBC, then plasma, then water, okay, bilirubin, many components are there. So we are interested to segregate those components. So how to do that? So we have taken the array value of the those blood component, and we have created the structure. This is called ring resonator structure, and this is called bend waveguide, and this is called uh, bus waveguide. Fine. So by creating the structure, and then we'll allow blood sample to pass. Then other end, yeah. Then other end, we will get the signature graph, which will be clear to you. Yeah, these are the result of the blood component analysis. You can see that for the biotic, these many blood component, biotin, then streptomine, then bovine serum, albumin, cytop, ethanol, glucose. So these all hemoglobin, blood plasma, okay, these all RA value we have collected from the literature survey, and then we have simulated, and then we got the different graph. So in place of adding all in the single graph, we have shown two at a time, so that we can say that so clear cut distinguish signature, I can say, of the biotin, of the bovine serum, or for cyto. These are the blood component, and we are getting the separate graph for the each blood component. And I will tell you now this citation is 36 now, current citation. Old data I am giving 19. So many people are giving the citation, and while my talk, I will suggest you how citation will be more of your paper. I will tell you. Those who are attendee, if they are publishing paper, it will be very useful for them, because if you are giving the RI value or anything you are giving, so that some other author will take your paper as a reference paper. Because why they will take your paper as a reference paper? Something should be there in your paper. So if refractive index, because they need to search for RA value. All photonics people are in the search of RA. If you will give RA value, definitely they will refer your paper, and they will quote your paper. So look, I have taken this biotin RA value, albumin RA value from this paper. So obviously your citation will keep on increasing. Here also we have done using the IPK software, which is the Python based, and then we have given the OWL vision for GDS2 for the PCRR photonic crystal ring resonator. Okay, so these two paper I told how we have used for the diabetic. Now optical sensor as a MEMS sensor. So now I told you photonic crystal we used. Now second category of sensor is MEMS sensor, where one mechanical student is working on this uh, PhD under me, and he's working because being mechanical, it is very easy for him to correlate this MEMS sensor And MOEMs, when we are talking, means MEMS, everybody know, micro electromechanical system. O will come means optical. So optical MEMS or MOEMs integrate the features of optical characteristics in MEMS. So advantage of MOEMs include no EMI interference, less size, already I told. Okay. So this paper was published in the TenCon, very good Asia conference. So in this, what work we have done? Performance analysis of optical MEMS based pressure sensor using ring resonator structure on circular diaphragm. So the purpose of doing this, I will show you. These are the diaphragm. See, I am not only giving the talk, but I am giving you this inspiration that you can work towards different category of photonic. And our main purpose is biomedical healthcare application, which is the today's topic. This topic I am not deviating. It is so only my other students are working on optical storage device and Indian Railway, but using fiber bracketing sensor. But I am only focusing on the biomedical healthcare. Okay, so coming to the biomedical healthcare, so this you can see that this structure in you by using the CATIA and ANSYS tool we have designed, where you can see inside there are two ring, three ring and one ring. Okay, double ring resonator integrated with photonic crystal, and this photonic crystal structure we have created by using the CATIA tool, and we have applied the pressure on this, and we are interested to see that where more deformation we are getting. So optical MEMS based pressure sensor name we have given. Then you may ask, where is the biomedical application? I will tell you. See, this is the diaphragm. So what we have done in the literature, this diaphragm can be used for tongue pressure measurement. I am talking to you, I am talking because my tongue pressure is very normal, okay, and how much it should exert, it is exerting, so that the pronunciation is very clear and you are able to understand. So to measure that, this is the very good device where it is very harmless and very thin slice is there, so that we are trying to find out how much pressure it will exert if it is double ring resonator integrated with photonic crystal. So this is a deformation. This is the ANSYS result. You know that in ANSYS, blue color is the red color is the higher pressure here, and surrounding is the low pressure. Deformation is the double ring resonator for applied pressure. This is the single ring for this. These are the design parameter. You can see diaphragm thickness is 0.23 micrometer. So it is very painless. Just you can put beneath your tongue and you can measure it. And the diameter of the hole size, all the parameters are mentioned here. So you can see that result of optical MEMS based pressure sensor. So different pressure is applied, and for the double ring and for the triple ring we are showing. Okay, just we are showing few example because a lot of slides are there, so single ring is not shown here. So finally, I will conclude. So what we have done, we have applied the same structure by using photonic crystal. Also, we have observed, and by using the applied pressure. So when we have applied pressure, then we have calculated the RI value, and that RI value we have given in the photonic crystal optical simulator, and then we have calculated the Q factor. So you can see Q factor for one ring resonator is 12,000, is very higher compared to the two ring structure and the three ring structure, and sensitivity is also very high. So what conclusion we got, that single ring resonator structure comprise more holes without uh, without creation of defect as per the mechanical behavior of any material. It means that if we have to use this for seeing the higher sensitivity and higher Q factor for the tongue pressure measurement, then we should use one ring structure where you are getting the high Q factor and high sensitivity. Fine. So next paper is published in SCI journal in John Wiley. Here also we have worked towards the optical MEMS. Uh, uh, I am in the second. I told 3, 4 photonic sensor I will talk about for biomedical healthcare. So this is for the second optical MEMS based micro cantilever sensor with various geometrical shape. So in this work, what we have done, we have designed a different shape of micro cantilever. You can see the micro cantilever, this is rectangular shape, okay, and in that photonic patches we have given. You can see that in the here you can see the photonic patches. So that is called optical sensing system, and we have done integration of that optical sensing system in the micro cantilever. Okay, integration of micro cantilever with optical sensing layer, and then further we have investigated for the micro cantilever for sensitivity and Q factor and minimum detectable limit. What actually we found that the optimum design of regular micro cantilever is considered during the analysis. The pressure is applied to the free end of the micro cantilever in the range of 100 to 250 kilopascal. The complete photonic sensing layer is analyzed. You can see in the center blue color photonic sensor layer was there, and we have given the pressure induced refractive index is calculated. I told when you will apply the pressure, then through the ANSYS tool and CATIA you can calculate the refractive index for equivalent maximum stress generated, and the result shows that remarkable Q have taken. Okay, so and Q factor also has been calculated, and sensitivity also calculated. So what we found that point least sensitivity 0.16 nanometer per kilopascal pressure is obtained for triangular micro cantilever in water medium. Okay, so what we have done, we have taken the three cantilever, we applied in the air medium and we applied for water medium. So why actually for this? So in biomedical application, if we want to use some sort of the viscous medium, then how it will look for the water medium? So which type of micro cantilever you should take for the biomedical application, and especially for the sensing biofluidic, because most of the biosample are in fluidic in nature. So we have compared with the, you can see next slide, see here, so air medium we have compared, this is for air medium, and you can see this is the rectangular profile, and this is the triangular profile, and this is for the trapezium, and we have seen for the air medium, we have seen for the, this is the trapezium profile, we have seen for the water medium. Okay, so this was the work. Next work is because lot of papers are there, and the next work we have done design and development of MEMS based optical sensor for biomedical application. In this particular work, it is by using the COMSOL multiphysics software, where we are trying to segregate the RBC and platelet. Okay, so sometimes you can segregate enzyme and protein. So it is very important sometime to segregate the two bio molecules. Okay, so we are trying to find out how to do that. So we have segregated, so that is known as by using the DEP, means dielectro plating technique. Okay, so in that technique what we have done, we have created a channel, then we have from the electrode we have tried to give the, we have applied the voltage, and we have seen that when it is getting the segregation of the RBC and platelet will start. I'll show you. So a dielectric particle experience a force on it under the influence of non-uniform electric field. This is the third type of photonic sensor I'm talking about. It is MEMS, but it is a microfluidic channel. Okay, so it is a third type of photonic sensor. So I'm giving the idea for taking the research topic. One topic you can take, you can select for your research purpose. So here, COMSOL Multiphysics is a very good software. It is available with the license version, and even for the crack version is also available. So in COMSOL multiphysics, you have to take the wave optics. Okay, acousto optics are there. So a lot of modules are there like RSoft, we have beam prop, mod getting, full wave. In the same way, functional multiphysics is also having lot of tool. So we are using the here microfluidic tool. So here the RBC are subjected to the larger dielectrophoresis DEP force than the platelet because of its larger size. So it depends on the size also, and due to this reason RBC deflect more in the applied field than the platelet, and physical parameters of the electrode like shape and size is changed, okay, which is more visible with this. You can see that this is the microfluidic channel, okay, and these are the four port, okay, input port and output port, and here are the corrugated structure. Now we are giving the voltage here, and so this corrugated structure, people are working towards different type of structure, triangular, sawtooth, and they will see the output, and they will calculate the sensitivity, and they will see that how minimum voltage the if achievement is in minimum voltage, how you are able to segregate. So one outlet it will come RBC, and one outlet it will come the platelet. You can see that here comparative analysis has been done. All the three structure we have done. One is the triangular structure, and another one is the sawtooth structure, and their corrugation is very small. And for all those structure in COMSOL, we have done the different microfluidic device. We can give the name for the blood component segregation, and in blood component we have chosen RBC and platelet. So what we found that comparison table shows the result that if the corrugated structure is square, or you can say electrode shape, then height of the electrode shape we have taken 40, triangular 60, and right triangular 40, wave shaped, means sawtooth, and width of the electrode, number of electrodes we have used, how many, and difference between the electrode, what we have kept, and separation voltage, what we got, okay, and we compare our result with the existing paper, and we found that in the compared to the existing paper, compared to that in less voltage, we are able to segregate that. So microfluidic device can effectively segregate the different blood components, and DEP dielectrophoresis method can be used for cell separation, and shape and physical dimension of electrode affects the cell separation. Yes, as I told that the RBC size is diameter is more, so based on that also it will depends on the cell separation, that how much voltage is required, and optimization of the device for minimum voltage required is one of the criteria for cell viability. So people are working towards this for less minimum voltage should be required for segregation. That is one type of work, which I told the third term. And this is for a cantilever again for the MEMS, means second type of sensor. This paper is published in the Optic Journal, which is ACI journal. This is for the early detection of the cancer. Here you can see that WIMPs based cantilever sensor for early detection of cancer. So you can see here also we have taken rectangular cantilever and triangular. So design of photonic patches are there, which is called photonic sensor patches, which is integrated in a square and triangular cantilever structure. So design of photonic resonator based integrated micro cantilever sensor, and then we have designed different shape. As I mentioned here, you can see rectangular and triangular shape, and optomechanical analysis of the sensing device for cancer. Optomechanical, when we are talking, it means photonic sensor we are using as a, you can use RSoft or you can use MEEP tool. Okay, so these are the, photonic crystals. So separately you can work for this, you can write a code for that, and you will get this flower type structure. When you can see that this 1 2 3 4 5 6, it looks like a flower type structure. So but it is a ring resonator structure where you have created the waveguide, okay, by leaving the scattering rod in between, and the size is 33 micrometer to 21 micrometer, where in this design you have taken lattice constant A 0.5 micrometer, radius of the hole 0.13 micrometer. Okay, from here light source, and here you will get the output. So this is the optical spectrum analyzer. You can give the output source. So what we have done here, we have done the optomechanical analysis. When we are talking about optomechanical analysis, it means actually we are using the optical tool. As I told you, you can use MAP tool, you can use RSoft, you can use numerical, whatever facility you are having. And optomechanical. Mechanical means when you are using this, then how much pressure you are applying at the other end, it will be mechanical. So by using the ANSYS tool, you can able to do that. Okay, so it is known as the optomechanical analysis. Okay, so if you are applying the pressure, then you can calculate the stress and strain, and by using the formula you can calculate the RA value. So investigation of sensor device, we have done performance, sensitivity and Q factor. Range of pressure exerted on microcantilever due to binding of carcinoembryonic antigen molecule. This was the requirement for the early detection of cancer. We got in one paper where they were mentioning that if you have catch hold of carcinoembryonic antigen molecule on the surface, then you can able to predict that the person will suffer in future about with the cancer. Okay, so this is a very good experiment we have done, simulation on surface microcantilever we have calculated. So by FEA analysis, by finite element mechanical tool, simulation were carried out to obtain the surface stress on microcantilever, and finite difference time domain is used. Whatever MEP or numerical or RShort, the basic algorithm is finite difference time domain method are used to obtain the transmission characteristics of photonic resonator structure and the range of pressure exerted on microcantilever due to binding of carcinoembryonic antigen molecules on surface microcantilever is calculated. So we have calculated for 0 to 2 megapascal of specific number of molecules which we got. Why between this range we should calculate? It was given in the literature survey of for early detection of the cancer. And high resolution with high quality factor and pressure sensitivity of 60 nanometer per megapascal is obtained for triangular microcantilever profile. Regular rectangular microcantilever has shown sensitivity of 0.01. So it means that it is very less sensitivity it is showing when we are using the uh, regular microcantilever. So we should use triangular microcantilever where we are getting the higher sensitivity and high quality factor. Quality factor is 11,000. Okay, in the range of 11,000, whereas here for using by using the triangular cantilever you are getting 3,000 range or 35,000, 38,000. 38 3,805, so it is less. So obviously we should go for high quality factor, and both the sensor configuration has shown transmission efficiency above 90%. Thus a novel photonic resonator based microcantilever sensor uh, has been done, which is very promising in the and we got very good comments from the uh, reviewers that it is a very unique work where we are using the micro cantilever or using the CEA, that carcinoembryonic antigen calculation. So little bit bio portion we are showing just to give the idea that how you should work towards that. If you will see for cancer, you don't see by which method they have done. You just take that paper and you calculate how much pressure it will exert, then blood flow when it will go, then how much pressure it will exert, and that pressure you take the value and you put in the simulation of RSoft or whatever Photonic crystal. During analysis, you assume that 1 nanogram of carcinoembryonic antigen binded to the surface of the microcantilever, and 1 nanogram of CEA will include this much pascal of pressure, which we got it. And from the literature, it is obtained that weight of carcinoembryonic antigen molecule will be this much Dalton. So we have converted this Dalton into almost nanogram. So we are getting 3 nanogram. So we have done the calculation for that. By considering above calculation, pressure range, we got this. Right? So which we have considered why we are taking this pressure range. If you want to publish paper in SCI, you should be very clear what you are doing. If you are not clear, then reviewer comments will come. You have to say why you are considering this much pressure range, why you are doing. So your calculation part should be very clear. If you want to hide in the paper, you can hide, no problem. But in reviewer comments, it will be asked. That time you have to give the everything. So you should be ready with the your all the values, right? So these are the result of MOEM's cantilever sensor. So you can see that uh, you are applying the pressure for the different pressure you are applying, okay, and efficiency also is shown for the different wavelength and for the different pressure range. You can see that, okay, for all the different cantilever. It is fine. So now, what is your final result? You can see here pressure when you are applying 0.5 megapascal, then 1 megapascal, then 1.5 megapascal between two. This why these two pressures between this range already I told, because of carcinoembryonic antigen molecule. It will exert this much pressure. Okay, so we are getting the distinguished wavelength shift, and we are calculating the Q factor, and we are calculating the transmission efficiency in percentage. Next paper, this also in published in Nanophotonics, where we are working on the same. We are working on the brain tumor, where silicon nanostructure based photonic MEM sensor for biosensing application. So you can see that here, here it is. Okay, this is the rectangular, and design of different shape of micro cantilever has been done, and design of optical sensing mechanism. Okay, this is the photonic sensor patches, and integration of micro cantilever with optical sensing layer, investigation sensing capability optical micro cantilever sensor, such as, again we have find out only difference is the structure. Okay, the structure we have given the different structure, different mechanical structure, and this is the fixed end of the micro cantilever. You have to give for the answers fixed end and the free end. This is the free end, where it will exert if this blood flow is there, and this will exert how much pressure. This we have calculated. Because of that, we have calculated the stress and strain. So RI value we have calculated. And we have done for the applied pressure for the regular rectangular cantilever, and for the triangular cantilever we have applied, and this is the ANSYS result. You can see that ANSYS workbench. So what information we have? So you can see that transmission spectrum, okay, uh, data for V shape uh, micro cantilever with this pressure. Okay, wavelength shift is this, and maximum pressure sensitivity you are getting 39 nanometer per megapascal. Q factor is 12,885, and this is transmission spectrum data for rectangular shape micro cantilever, where you are getting very less sensitivity. Okay, for the rectangular you are getting less sensitivity and less Q factor also. So we are comparison of proposed sensor with the reported sensor. So these are the structure with which we have done the comparison. In 2017, somebody worked on the point effect resonant microcavity, where this was the sensitivity 15.8, and then 18 they have done microcantilever integrated photonic crystal resonator and sensitivity, then two-dimensional photonic crystal sensor for pressure sensor. Okay, okay, this is for our, okay, for the T shape microcantilever and for B shape and U shape. So we got this. See, if this work was accepted in nanophotonics because of the detailed work analysis, clear concept, and with the comparison with the latest up to the 2020 paper. These are the benefit of attending this type of workshop, where you will come to know why your paper is getting rejected from the high, you know, impact factor journal or SCI journal or transaction. Now fourth category of sensor I am showing now. This is the last. Optical sensor as SPR sensor. SPR means surface plasmonic resonance sensor. Here, my two students are working on this SPR sensor. SPR, further I have divided these two students into two topics. One student is working on the biosensor, other one is working on the optical storage. So we are using SPR. So what is SPR? Just few introduction about SPR. SPR is a technique for detecting changes in the refractive index at the surface of the sensor. Okay, same thing it will do. So light passes through the substrate layer and is reflected off from the gold coating. At certain angle of incidence, the surface plasmonic wave is created. So this phenomenon is used for diagnosis of certain disease. SPR is well known surface sensitive spectroscopic technique. Okay, so some people are using for the blood sugar, some people are using for different disease. So this is for the diagnosis of the blood sugar. So you can see photonic crystal also we are using for the blood sugar detection. Okay, and this is for the SPR design. So here we are using RSoft. RSoft only we have done SPR, but anyone want they can do numerical also and photonic crystal. So here it's a layer by layer structure. So you can see that this is the substrate layer. On that it is a blue color. This is the substrate silica layer, and this is SiO2. Okay, and this is the gold layer. So what is SPR? In SPR, wherever there is a metal dielectric interface, this is metal gold and this is dielectric. So whenever metal dielectric interface and light will allow to pass, then it will excite the electron on the top surface. Top surface means here the top surface. Okay, so this surface, what will happen? Oscillating electrons. These oscillating electrons are known as the plasmons. Okay, so you understood what is plasmon? Plasmons are nothing but these are the excited electrons or oscillating electrons. It is caused because of metal dielectric interface. Okay, when it is excited by the, you know, uh, light. And on the plasmon we will allow our biosample to set or analyte. Okay, so here you can see that how light is passing. Light is confined. We have to first look for the confinement of the light, and further we will see. So this is the structure. You can see the dimension is mentioned here. Free space wavelength, index difference is this much, and background index is 1, and width is this. This is the way our shop will work, where in the symbol we have to give the different design parameters we have to give. Okay, and then we will run the simulation. So after simulation, we are getting the two different graph, which is showing that two different refractive index. One is for normal and one is for the sugar sensitive blood sample. Okay, then we are getting very. This is the resonance peak graph. This U-shaped graph I am telling. So resonance peak, and from here we can find out the sensitivity. Okay, so we have calculated the sensitivity 357.14 nanometer per RIU, and this is the second structure. Okay, second design, where we have changed the design. Okay, and by changing the design, here I will give you one idea. uh, Substrate layer thickness also you can change, or you can do with substrate and without substrate, and you can see the sensitivity. Okay, and by considering any biosample. So here we have changed the thickness, and in this design parameter, and we have seen some shift different distinguish. It is more distinguished than the previous one. So we keep changing and we keep observing what is the sensitivity, and sensitivity also enhanced now 714. So if it is more distinct graph, this is what we are looking for to separate from the normal to the blood sugar affected sample. Okay, and we have the third design. Okay, so in the all we keep changing the thickness, we keep changing the material, we keep changing the different analyte. Okay, and here also we have shown, here we have taken silver layer because for plasmonic, you know, metal dielectric interface. So metal is aluminum also, metal is silver also. This time we have considered the silver. Okay, silver in place of the gold, and then we have done the simulation, and we got the little less sensitivity compared to the gold. Okay, so we are getting the different wavelength shift. So we have done for thickness of 0.074, both gold and silver sensitivity remain same, but we do prefer gold than silver because silver has pronounced instability problem. Okay, so for that particular thickness, next level anybody want, they can change the thickness only. You can change the thickness of the gold layer, you can change the thickness of the silver layer, then you see whether we are getting the same sensitivity or not. This particular thickness we have got, so we have reported this one. Next our, here we have done very unique structure. We have created two box, you can see that, and at a time it is for the cross sensitivity. Suppose if a person is suffering from AIDS or HIV positive or HIV negative, so we have a channel A and channel B. So in channel A we will maintain the RI value of HIV positive, and channel B we will put RI value of HIV negative. So if unknown patient will come, so where it will fall, we can able to predict that you are HIV positive or HIV negative. Okay, so at a time we can use this for the cross sensitivity. This is I got this inspiration by using, by seeing that fiber bracketing sensor. Fiber bracketing sensor they are using for simultaneous measurement of temperature and pressure. So for by that I thought that we can create a dual channel uh, based optical waveguide sensor. So it is very good appreciation we got from the site conference in US. They called me also for US travel for the presentation of this work because they were very happy with this structure. And it is the beauty of the plasmonic structure is in the same foundry you can fabricate it because it's a layer by layer deposition. So it is the same VLSI lab. Wherever VLSI structure, VLSI design you are fabricating, the same foundry you can use this. And these are the substrate thickness and oxide layer and core and cladding, each and everything we have given here for this particular structure. And the working principle is the sensor as shown in the optimized to operate in an aqueous environment. Aqueous environment, when we are telling that, it means that liquid, we have taken the biosample with device parameters of thickness TAU 5 nanometer and LSPR plasmonic structure thickness 10 micrometer, and broadband source we have used. Okay, 1.33 the 1.34 refractive index change is there from this analyte, and a change in the refractive index due to binding of analyte molecules. So what actually happened here, I will tell you. No need to read this. On the top of the plasmon where we are putting our sample, okay, so top surface of the plasmonic layer, then what is happening? There is okay, there is a very strong interaction of the biomolecules, and this is called adsorption, not absorption. The difference between AD and AB is adsorption will be localized field. So SPR is working on adsorption rather than absorption. So adsorption will go in the detail of the depth of the four layer, and where we can, so when light will allow to fall on this, and light will couple with that, and we will get a reflected light which will carry the information of whatever we kept on the top layer. So this is what this is why SPR is very very sensitive for the biosensor. So these are the cross sensitivity result for the HIV positive and HIV negative. Okay, and this figure shows the due to binding of analyte to the biomolecular recognition, that is BRE, has resulted in change on the light is allowed to fall on the top surface. Then what happened, incident light is known as the Ki, and on the top there is a oscillating electrons. Okay, that resonance, that is the Kp. So whenever Ki is the Kp is for the plasmonic resonance frequency, Ki is for the incident of light frequency. When these two will match, then only you will get the resonance. Okay, and you will get this graph. So you understood why this graph is coming. This graph is coming at which point Ki is equal to Kp, means the K is the wave vector, which is the 2 pi by lambda, or you can say the uh, frequency. Okay, so when the incident and the resonant plasmonic frequency both are same, then resonance will happen, and change in propagation constant result in shift of the wavelength. Thus the binding between the analyte and the biomolecules is measured in terms of shift in the wavelength. So finally I finished my talk, and I am happy to share any question if you know the, if you ask any question. So four type of basically sensor I talk today for your if you want to select any research topic. So there are in photonic four type of sensor. I discussed photonic crystal based biosensor, then MEMS based biosensor, then microfluidic based biosensor, it comes out, and then finally the SPR based biosensor. So thank you very much for giving me this opportunity.
Yes, thank you, madam, for such a wonderful description of your research work done here. So, participant side, if anyone is having questions, you can just ask, madam.
If any participant want to collaborate with me or any question, you can write me mail also. How much possible, we will give the answer. And for especially, I will suggest for SCI paper, what you have to do, you have to give end-to-end product. If only you are working nowadays, because as lot of people are working in this domain, so they are rejecting the paper very frequently, because you are only working on the sensing layer. Somebody will work on photonic crystal, they will not talk about input side and output side, whereas people are looking for the device level. That's why I was showing you IPK software. Using IPK software, we are showing the total device in the chip, how it will look like. Or else you integrate two software. Like we were using the ANSYS tool for using the mechanical pressure. So mechanical ANSYS tool, we have integrated with the photonic tool. This is what my own idea. So I keep doing, because with the comments, I want to improve myself. Reviewer comments are very important. I'm very happy whenever I'm getting the reviewer comments, because they will write very critical comments. They will write no novelty already, because of the RI value shift in the wavelength. Lot of people are working. What is new in your work? So by seeing that, we will get idea and we keep doing the changes. And then we are surprised to tell you nowadays only SCI paper we are publishing. No Scopus. We stopped publishing Scopus paper long back now because of this idea. And I am this my secret I am revealing in front of Triveni ma'am so that you
Oh,
can publish any paper in the SCI journal. You have to club two software. This is the main secret. In easy way, I'm telling you. Mechanical to collaborate with the your photonics too. Then it will be definitely chances are some novelty, some uniqueness, so that people will be interested to read your paper. This is what recently JOSA also our group has published paper. JOSA is very good journal. Yeah. There are also SPR paper.
thank you, madam, for such a wonderful talk for both the sessions on quantum as well as in photonic sensors. I think the participants have taken the gain the knowledge in this field, and hope they will be motivated to do more research in your area. I think thank you, madam. Thank you very much, madam.
Thanks.